Counting and logical ability. I started off with using Ubabooga's LLM launching website. I started at home, but quickly moved to a hosted solution. I was using RunPod and a GPU that could handle 24 gigabytes of GPU VRAM. I was using Llama 2, 13 billion node version, and I was using LoRa. My goal was to represent simple ping images as ASCII art and then show them to the LLM and have the LLM identify them. I wanted to do fine-tuning to learn a task involving the ASCII art I just mentioned. Additionally, my images were all of a similar variety. They all contained collections of dots. It seemed to me that LLMs could count, or seem to count, but that ability might be derived from the symbol of the number in question, not the real number itself. An LLM might not truly know what a symbol like a number written in a text file also had the meaning of a true number. The purpose of the images was to have the LLM count the few dots in the image. LLMs may have the ability to count, but they may not, and it seemed to me to be an interesting experiment to see if I could get the model to count small integers from simple ping files. There is, or there appears to be, a functionality in Ubabooga to include images in individual queries. This method would be far superior because it uses the image in a query but does not use the ASCII art. The unfortunate part of this is that when you're doing training, the functionality in question is not available. In other words, you can use an image during a query but not during training. I think this is the case. This was the case when I was looking at it before. I'm a Linux user, so in Python I made a GTK3 GUI that I could use for generating a training set. My training sets generally had 3,000 examples. I had the program generate ping images randomly that contained a number of black splotches or dots. The number of dots varied randomly from 0 to 9. Then I had my code take a version of the ping and convert it to ASCII art and include it in the various training question-answer pairs. A training run took between 1 and 3 hours. There were several serious challenges to this methodology. One of the main challenges has to do with the LLM concept itself. Before an LLM processes a piece of text, it needs to be tokenized. Tokens sometimes take several symbols and combine them to make one unit. Pictures like pings or JPEGs need to represent visual data as pixels, spots or dots that have different intensities. These dots also need to be evenly spaced. Also, the tokenization task is not clearly visible to the human user. What this means is that lines of ASCII art can be converted to tokens that do not really reflect the nature of the original pixels. And even further, one line in an ASCII art example could be tokenized to some data that is not the same length as a previous line might be tokenized. The concept of space or distance in the horizontal direction in an image is lost during the tokenization. And vertical distance is lost too, as the lines, once tokenized, are treated separately by the model. This vertical challenge is mostly what is being challenged in the training I described here. There are other problems as well. The fine-tuning process does not automatically take into account that ASCII art input is large, symbol-wise, during training. The window needs to be large enough to evaluate a complete ASCII example with each question-answer pair. The larger this window, the longer training takes. This is also related to the fact that I'm using LoRa for my fine-tuning. The R in LoRa stands for rank, and this is the window I was referring to above. If the model understood the task, it could easily approach the problem by counting the times in the overall image where the information deviates from the normal. In other words, if it knew the size of the image and the token for the background, it could count the number of tokens that deviated from the background, and it would have an approximation of the answer. This could be a good start. The problem would be, in that case, that there are some splotches that traverse several lines. Still, any outcome like this would have been welcomed, but this was never achieved. It would be pretty encouraging if the model even did this, if it came up with some number, but it didn't. This does not mean that the model has a misrepresented view of small integers. It just means that it cannot understand ping files in ASCII art form. It's probably safe to assume that the model cannot understand anything in ASCII art form. Furthermore, the model cannot be trained using LoRA to do this understanding. LoRA stands for low rank adaptation. From my limited understanding, a large language model is modified by placing a low rank matrix between every two layers in the model. By rank here we mean size. It may be that with Llama 2 and the standard LoRA implementation, the task I'm looking to perform cannot be achieved. For this reason, we modify the task and try again. In the following text, we describe a second experiment that could be more successful. So here we fast forward to the present. We will attempt, for at least one experiment, to remove ASCII art from the training and prompting. We will define a string of characters that has a number of countable symbols in it. We ask the large language model to count the number of symbols before and after LoRA training. First, we do the experiment without the training step. And a spoiler for later, we don't do any training because the results were poor. Hopefully, the model will get it right. If the model gets it right before training, then we are done. Results. The same model was loaded as before. No training is being done. We have 4 sets of prompts and we use them all. Each of the 4 uses slightly different wording, but has 10 possible answers. The integers between 0 and 9. The first set looks like this and should be answered by the number 3. Again, the answer should be 3. Just for completeness, here is another in the same set. For this one, the answer should be 5. We call this the single example small prompt. With these prompts, we achieve a correct answer for 1 through 4. In other words, the model got 0 wrong and it got 5 through 9 wrong. The next series would be called the double example small prompt. What we're doing here is offering the model 2 examples and asking it to fill out the integer in the second example only. This is a sample of double example small prompt version. The answer here should be 5. With this series, the model got good scores. It succeeded in identifying the numbers 0 through 8. It only got the number 9 wrong. The next series is called the symbol example large prompt. None of the large prompt examples got good output. The single example large prompt was not correct for any input. The double example large prompt was correct for the integers 0 and 1. No others were correct. So this is the single example large prompt. And then the answer to that should be 3. And then here's the double example large prompt. The example should lead the model to reply with 4. Since so few answers were found with the large prompt examples, we consider them a failure. Possibly if we use different separator character, the results would be better. These examples are easily read by people and apparently not easily read by this computer model. Conclusions. In some of the examples, the models seems to count, and in some it seems unable. I feel the model cannot count, but recognizes groups of characters together and associates them with a simple number. Others might disagree, but I think the knowledge of an array that contains 2 items is hard-coded into the model, and that it cannot count to 2.